Okay, so now we're going to have a look at an example of what I just talked about as a theory. So the previous video, no numbers, just the ideas. Here we'll actually do an example. So let's go for find a maximum, or maximum, there might be more than one, minima points of inflection, spelled differently this time, either spelling is acceptable. And together those things you'll often see them referred to as stationary points, just language of, and we'll make up a curve, 2x cubed minus 3x squared minus 36x plus 4. Should have a y equals if it's an equation, so we need an equals in the other half of the equation. Okay, so we're going to have this graph, and we're going to try and find where the maxima and the minima and the points of inflection are. And we don't even have to be able to draw the graph. And if we can draw the graph, it might be a little bit helpful, but you don't need to be able to. I mean, that one's a cubic, so it's going to look something like that, roughly how it looks. Where this point will be 4. I know that point, that's easy, because if x is equal to 0, all of these things go out and y is equal to 4. So we know that much. And the question we really want to know is where's the minimum point and the maximum point, and is there a point of inflection in the middle here somewhere as well? Okay, so how do we do this? Well, the key thing is that the turning points, and this is usually worth writing, there's a mark in an exam, turning points occur where the derivative, in this case dy by dx, equals 0. And as soon as you write that, you should think, oh, I need to work out dy by dx. So we've got our function over here, so let's just differentiate the sucker. So dy by dx, which I need to make the equation work. If I differentiate this thing, what do I get? I get 6x squared minus 6x minus 36. Okay, so that's the derivative of this function. And then I know that turning points occur where that equals 0. So dy by dx equals 0 means that this thing has to equal 0. Yep, and then it's just a matter of solving that. So just a little bit of algebra to solve that. As you look at it, you should be thinking to yourself quadratic, and then you should maybe be thinking to yourself factorization, or if you can't factor it, then you'd go and use the quadratic formula. But I can factor that. It's got a 6 for a start, so let's take that 6 out the front of the whole thing. Minus 6 equals 0. And that's just what you got, negative 3 and plus 2. So x equals 3 or x equals negative 2. So those are the x ordinates of the turning points. So we know that this point here is that when x equals 3, and this point here is when x equals negative 2. We have the values for those. When it says find the maximum or minimum points, it doesn't just want the x part, it wants the y part. You haven't found this point, you've only found how far along this way it is. To find the actual point, you need to figure out what that is as well. And likewise up here, you need to figure out what that is as well. Which means you've got to plug your number back into the equation. So you've got to put 3 back into this equation and work out what that bottom point is. So what's that going to be? 2754 minus 27 is 27 minus 108 is negative 81 plus 4, maybe negative 77. I'm doing that off the top of my head, so for goodness sake, check that. It could turn out to be complete rubbish, but grab your calculator and check it. And same for negative 2. So we have negative 16 minus 12 is negative 28 plus 72 is 44, and 4 is another 48. And maybe 48 up there. Again, check it. Those things are important. So we would say here the turning points are 3, negative 77, and negative 2, 48. Okay, so we've actually got the values for the turning points. In this case, because I've sketched the graph, we know which is the maximum, which is the minimum. And also, I mean, 77 negative is less than 48 positive, so that one's got to be smaller than that one. So you get some sort of feel for what's going on. But if you can't sketch the graph, or you've got a really weird one, and you're not quite sure which is the maximum and which is the minimum, or if you've only got one answer, if this came out to be linear and not quadratic and you only had one answer, is it a maximum or is it a minimum? And how do you find that out? So we need to be able to find the nature of these turning points. And to do that, we need to use the second derivative. So if you're not sure, look back on the previous video, but I said that maximum occurred where the second derivative is less than 0, minima occur where the second derivative, oops, I lost my square there, is greater than 0, and points of inflection are where the second derivative equals 0. So the first thing we need is the second derivative. And the second derivative is just the derivative of the first derivative. So this is our first derivative. Yep. So we just differentiate that sucker, and that'll give us the second derivative. So the second derivative, I differentiate this one, what do I get? I get 12x minus 6. So that's a nice simple function for the second derivative. And then all I need to do is chuck in my x values and see whether it's less than or greater than or equal to 0. So let's do that. So when x equals 3, my second derivative is 12 lots of 3 minus 6. Just putting my 3 into where I had x. I'll say 36 minus 6 is 30, which is certainly bigger than 0. So that one's a minimum, which makes sense. So when x equals 3, I'm claiming there's a minimum, which we have. It does seem to work. And when x equals negative 2, my second derivative is 12 lots of negative 2 minus 6. Negative 24 minus 6 is negative 30, less than 0. And if it's less than 0, we know we have a maximum. If it's less than 0, we have a maximum. So again, I'm claiming when x equals negative 2, I have a maximum. It seems to work out pretty well. And the other thing is, for the point of inflection, the second derivative has to equal 0. So second derivative is 12x minus 6 has to equal 0, but a simple math tells us that x equals a half. So the point of inflection occurs when x equals 1/2, which on this scale probably isn't exactly that point, but it's somewhere close to that. I haven't drawn a particularly good diagram, but somewhere in there will be the point of inflection. And that's where it changes from being concave down to being concave up. Okay? So using this technique of calculus, of differentiation, we can figure out where the biggest point is, where the smallest point is, and where the points of inflection. Notice these things are local maxima and local minima. This isn't the highest value the function ever takes. The highest value the function ever takes, it definitely gets higher here than it was there. So it's only in that local area it maximizes. Same here, the local minimum, actually that, yeah, this goes further down there. But it's quite a neat tool that gives us a way to get at the points of interest without actually having to be able to draw the graph. So maximum, minimum, points